So today we shall begin with the fifth module in our syllabus, that is network functions. Compared to other four modules which we had considered, this module is more analytical and you are supposed to give close attention in order to understand the significance. Most of the things would be highly mathematical, even though I am trying to demathematize it, in the sense that I will try to explain again in very simple terms in order to see that every individual understands something partially. So, network functions are essentially the functions of complex variable S. These are functions of complex variable S. How do they arise? What is their significance? What are different types of functions? Based on the nature of functions, how we can characterize the system, all these things will come in due course of time. So, essentially, we consider electrical network. In general, we are having a big electrical network which does not include independent sources. Then you can take any 2 points that comprise a port. Electrical network is a combination of R, L and C and dependent sources. This is the entire network. So the first very simple network function which we consider, that is applicable for even one port network. One very simple network function ultimate. Once you go through preliminaries, ultimately it is dealing with one polynomial in the numerator and another polynomial in the denominator in terms of S. But so as to get good idea about what that corresponds to, we should go step by step and we should understand each and every theme in development of these network functions. So for a one port network, we are having the transform impedance. This may be any complex circuit. So when we look towards the circuit from this port, so we are defining the first network function, that is the transform impedance. That is ZS. Transform impedance, that is ZS, is what means, suppose if we will revisit the Laplace transform we will explain its significance. We will explain it in some other ways also. So if we are having this as Vt, sorry, if we are having the voltage here as Vt, this current is It, voltage is Vt, current is It, then if we transform this Vt and It in the Laplace transforms, that is Vs and Is, and then take a ratio of Vs upon Is, and then take a ratio of Vs upon Is, that is called as transform impedance. That is called as direct impedance cannot be taken. Direct impedance cannot be taken. Therefore, impedance is the ratio of voltage and current. Transform impedance is the ratio of Laplace transform of voltage and Laplace transform of current. Laplace transform is something about which the understanding process of an individual at the second year of undergraduate course is not crystallized. What I said right now? What I said? If we have to teach classically, it means that deliver everything with a very fluent English without any interruption and without bothering whether is it having any impact as regards to understanding, right? That we usually discourage. Therefore, I will try my best to ensure that we understand something. So, considering it in transform domain doesn't provide us a good handle because we do not have that much comfort on using Laplace transform for analysis purpose. We have a comfort as regards to using Laplace transform as a tool. Means, as you can solve the differential equation by conventional way or by the way which we assume, or by that is a cos t plus a cos omega t plus b sin omega t like, or by Laplace transform, we come to the answer. So Laplace transform is well perceived as a tool, but its understanding is not so profound that we understand all these things immediately. Therefore, we will have an alternate view on this ZS. We will have an alternate view on this ZS. So ultimately, this would be a circuit which will consist of R, L and C and maybe dependent sources. Right now we don't stress on that. So it is a circuit consisting of R, L and C, which are linear devices. Now, again it is a repetition in some sense that we have discussed it before, but might not have understood because these are the concepts which require many iterations of listening, reading, talking, writing, thinking and dreaming. After many such iterations, it is likely that few of you may get enlightened to have some kind of idea that they feel that I have understood. So we are looking at this circuit which is containing linear components. Linear components means they exhibit linear relationship between voltage and current in their direct form or their differentials. Resistor is a linear device because voltage across it and current through it are some ratio. These two are having a linear relationship. Capacitor is a linear device because voltage across it in differential form with respect to time and current through it are linear. As regards to inductor, differential of current and voltage are linear. So now as linear components are there in the system, we try to analyze the system, we try to describe the system by a single figure. That is the interrelationship between voltage and current in the form of impedance. I again repeat, it's a complex network, but when I am looking from 2 points, I only look an impedance. When I look towards a very complex system, it is ultimately some kind of combinations of R, L and C. So what effectively I should see is a single value. Any complex electrical system can be considered to be just an impedance. So the complete network between the 2 points is nothing but an impedance. So it is an equivalent impedance seen by me between these 2 points. Again, the issue becomes like the same which we were discussing even for a single capacitor or single inductor. But what is an impedance? What is an impedance? It is the ratio between voltage and current. When we define a ratio, usually when we were having DC circuit analysis of resistance only, when we apply some voltage, the voltage when the things stabilize in a system, then voltage across any 2 point remains constant and also current remains constant. Even though current is rate of flow of charge, that rate remains constant. So connecting 2 volts across 1 kilo ohm resistance leads to 2 milliamperes of current. So 2 volt is voltage across it and 1 milliampere is the current through it. So So V is 2 and current is 0.002. So V upon I is 1000. That is the resistance we can say. For resistor, even if we change the voltage, the proportionate current is immediately changed. So always the ratio is constant. Is situated for resistor. But the situation is not same for inductor and capacitor. If we apply a sinusoidal voltage to inductor and capacitor, we will find what will be the case. If we apply a sine wave across an inductor, I will get current as a phase shifted wave by 90. Similarly for capacitor also, I will get the current which is phase shifted by 90. The nature of shift would be exactly opposite to each other. But in that situation, the problem for defining impedance comes. And now I would like that you should share your ideas. You should answer the question now, that what is the problem in defining impedance for capacitor and inductor. So unless these ideas are very much clear, we are not in a position to pursue further. So I will put before you a very simple example, and I will ask you to find out what is the exact problem in defining the impedance. We have a sinusoidal source 5 cos 2t. 5 cos 2t is the sinusoidal source. We have connected it across a capacitor of 2 farad. We have connected it across a capacitor of 2 farad. Right? What will be the current? What will be the current? C dV by dt. So 2 into dV by dt minus, we should be flexible so that we should try to keep the thing simple. So there is 2, that is C, dV, that is again 10 cos 2, that is 20 cos 2. So dt is this, and so same would be here, and it comes out to be 20 cos 2. It comes out to be 20 cos 2t. Is it clear? Now the question is, the term impedance, which at one go describes the relative relationship between voltage across 2 points or across a device and current through the device. You getting me? Impedance is a term which describes the relationship between voltage across a device and current through the device by a single value. Are you getting me? It is some ratio. Now the problem before us is it is 20 cos 2t and Vt is 5 sin 2T. That is voltage across the capacitor, current through the capacitor. Now, how I can describe the relationship by a single term? Whether the problem is, I want to know whether I do not want a solution immediately from you. I want whether you are in a position to understand that the situation is problematic. Yes or no? So the question is now how to take the ratio. How to take the ratio. Then if we go straight forward, then Vt upon It, that is 1 by 4 tan 2t. 1 by 4 tan 2t. Right? Would be impedance. 1 by, is it alright? Have you heard an impedance like this any time? Yes. 1 by 4 tan 2t is the impedance of the capacitor over here. What is the problem now? What is the problem in this?
It will change according to T. It will change according to T.
It will change according to T. So impedance, which is supposed to be a constant figure in given situation for a given system, has become a function of time. And that has means it can be anything. Time is having the range from minus infinity to infinity. So substantially it defeats the very purpose of impedance is a term which describes a particular property. That property is the relative relationship between V and I by a single figure. By a single figure is important. In that situation then, this impedance defining it to be tan 2t or 1/4 tan 2t defeats the purpose because it itself is a function. It itself becomes a function. Then what is to be done? So problem, I hope many of you have partially understood what the problem is. Now let us move for the solution. How to move for the solution? If few of you are having a solution, then they can come here and in front of camera tell the solution. The solution. So what we want now, we want to describe the relationship between these two. So direct ratio was one crude attempt. We want to describe that we now have come to a conclusion that if 5 sin 2t is connected across capacitor, then the current flow is 10 cos 2t. I want to describe how in a single number or maybe two numbers, I can describe 5 sin 2t and 10 cos 2t are related to each other. I want a method by which I am in a position to describe the interrelationship of two sinusoids of same frequency. I want to know the manner in which the relationship between two sinusoids of same frequency can be described in a better way. Ratio is not the only way. There is a systematic way wherein by a single number, two-dimensional, or by two independent numbers, you can describe it immediately. Both are sinusoids of same frequency means for a given frequency, two terms describe a sinusoid. For a given frequency, two terms describe a sinusoid. What those are? For a given frequency, a sine wave of 50 hertz, how it is described? A sine wave of 50 hertz is not a unique description. There can be many such waves. So as to make this description unique, we need two more things. What those are? Amplitude and phase. So the relative relationship between the amplitudes of these two sinusoids and the phases of these two sinusoids can describe their, what we can say, relative relationship or ratio fully. So when we take the ratio of two sinusoids, we take the ratio of amplitudes and difference of phases. So rather than means you got to carry a misconception of tan because we wrote it to be cos 2t. I will just rewrite it independently or in a different way, alternatively. So Vt is 5 sin 2t and It I can write as 20 sin of 2t plus something. What is that? Cos t is sin t plus 90 or pi by 2, 90 degrees. Right? Okay. Is it right? And now if I ask you to take the ratio, then you will take 5 sin 2t upon 20 sin 2t plus 90. You will not come to tan. And then the ratio of two sinusoids is fully described. So there is an alternative ratio representation of two sinusoids by taking ratio of amplitudes and difference of phases. So it can be fully described in this way. A1 sin omega t plus phi 1 upon A2 sin omega t plus phi 2, that corresponds to A1 upon A2 angle phi 1 minus phi 2. So this is the ratio representation. So impedance of capacitor, now we can describe it as 1/4 angle minus 90 degrees. 1/4 angle minus 90 degrees. Now we make some small change. Instead of this square wave, we connect a triangular wave. Instead of square wave, we connect a triangular wave at the input. And after connecting triangular wave to input, compute impedance. Compute impedance of the capacitor if input applied is plus minus 1 volt peak to peak, 1 kilohertz triangular wave. Means one period is of 1 millisecond. By the time when all are thinking, I will have a recall of attendees. Number 5, 13, 16, 17,
Yes, sir.
20,
Yes, sir.
24, 27,
Yes, sir.
30,
Yes, sir.
31,
Yes, sir.
39,
Yes, sir.
40,
Present, sir.
42,
Yes, sir.
45,
Yes, sir.
46,
Yes, sir.
48,
Yes, sir.
54,
Yes, sir.
55, 60, 63,
Yes, sir.
65, 66, 72,
Yes, sir.
73,
Yes, sir.
75,
Yes, sir.
77. Was it there for the test? Huh? Cool. Listening music? He is not. Is that it, not two? So is left. What? He has cancelled or not? Where? When? EPS. EFF or EC1? What is the answer now? For triangular wave? For triangular wave or for square wave or for any other kind of wave, we cannot define impedance. We cannot define impedance because, what is the reason? What is the reason? Ratio? Equation? define impedance. What is the reason? That the current is differential of voltage into capacity. The current waveform, usually for DC we have both things constant. When waveform is sinusoidal, what we are having is differential of sinusoid is always a sinusoid, or integral of sinusoid is always a sinusoid of same frequency with different amplitude and different phase. So for capacitor, current is proportional to differential of voltage. When voltage is sinusoid, current is also a sinusoid of same frequency, and both are comparable because both are sinusoid waveforms of same frequency. But if the voltage is of some other type, then the current waveform is completely different in nature. So triangular, it is somewhat exponential is the output. So the two waveforms are so different in nature that it is not possible to describe them by a single number like a ratio. We cannot describe them. Even if the triangular is a regular nature waveform, its output is also a regular nature waveform. Those are so different that we cannot describe them by a single value. The retaining of the shape is only taking place for a sinusoid voltage. So sinusoid is having a peculiar characteristic, peculiar waveform. It's a peculiar function. It is called as analytic function. Therefore, sinusoid is a typical class of functions which allows us to have ratio-like expression for differentials too. For differential also, we can. I had not made any announcement for teamwork. So sinusoidal function is the only function as of now which allows us a ratio-like relationship for differential, or in other words, with making our brute force non-standard assumption. The moment at which we make our non-standard assumption coupled with the standard assumption of j square equal to -1, non-standard assumption is j sin omega t is cos omega t. The moment at which we do that, the things become much simpler. So Vt is pi sin 2t, and then It becomes, which is 20 cos t, that is 20 j sin 2t. And then immediately you can take the ratio, and ratio is 1/4j. Ratio is 1/4j. It provides us a simple way with which we can proceed. So d by dt, if we are having a sinusoid, functions as input, in that case I can replace d by dt operator by what? I can replace d by dt operator by what? D by dt operator in case of a sinusoid is replaced by what operator? If Vt is sin omega t. What is dVt by dt? Omega cos omega t. That is omega j sin omega t. That is j omega into Vt. So d by dt is j omega. So we should not write equal to. We should write as well. So for sinusoid analysis, differential operator is a scaling operator. Differential operator is a scaling operator. And what will be integral operator?
1 upon 0
Integral 0 to t dt.
minus 0
That operator is 1 upon reverse of differential. Since differential multiplied by j omega, integral divided by 1 upon j omega. And from that point of view then, impedance of capacitor becomes 1 upon j omega c. Why? Because Vt is sin omega t, It is c dVt by dt, but dVt by dt is j omega Vt only, and c is there. We have some Vt as say sin omega t. Then current is c dVt by dt. That is equal to c into j omega Vt. So ratio we take 1 upon j omega c. Ratio is 1 upon j omega c. That is impedance. In that way, we can define impedance for sinusoid. So impedance of sinusoid is voltage upon current 1 upon j omega c is 1 upon, keep it in mind that 1 upon j omega c. What that means? It means that amplitude of the current is omega, impedance is 1 upon j omega c or minus j omega c, we can also say. What that corresponds to impedance ratio. So voltage upon current is 1 upon j omega c means current is omega c times in amplitude than voltage and leads by 90 degrees. Ratio is what? 1 upon j omega c or minus j upon omega c means current is omega c times the voltage and j is indicator of phase shift of 90. J sin omega t equal to cos omega t indicate there is a phase relationship of 90. J is a tool we have used to describe the phase relationship. We will be taking a break and I am going to continue, and next lecture will be DSA lecture. So we take a comfort break.